Hi and welcome to TRX Bench. This is a power supply for ham radio and anyone knows it, nothing special. But have you heard about the fact that this power supply can blow your radio? If not, this is the right video to watch for you. Okay, you want more details to avoid this power supply killing your radio? Okay, then simply sit back, relax and follow me along. Well, okay, you may already wonder why a normal power supply is able to blow your radio. So what we want to do is we just want to try to understand why a power supply like this, and this is a linear power supply, and we all prefer linear power supplies versus switching mode power supplies, because we know that the voltage is much cleaner and we do not have high frequency distortion and such. So normally we all prefer this linear power supplies, also they are much heavier. I mean, this is only a 10 amp linear power supply, but yeah, already this 10 amps linear power supply is quite heavy compared to the switching mode power supply. And even this power supply definitely have a much cleaner output voltage. There is, after all, a risk that especially these linear power supplies are really able to kill your radio. And the question is, how can that happen? Well, and just for a basic understanding, I have here the schematic, the basic schematic of a linear power supply. So we have here our bridge rectifier. So in front of the bridge rectifier we have normally our transformer who is transforming from 220 or 110 volt AC to, I don't know, 30 volt AC. Then we have our rectifier, and then we have here our filter caps, and then we have our power transistor, and connected to the base of our power transistor we have our electronic, which is able to adjust our output voltage, right? And that means that at the collector of our power transistor we have really the whole voltage which is coming from our transformer, and which is now here at our filter caps. And this voltage is of course higher than the voltage we will have here at our output. So at our output we expect to have 13.8 volt. So that is, or now what have we here on the front? It's telling us 13.5. So that is fine, and that is what we expect. But what is if this power transistor is suddenly shorting? And if that happens, then the whole voltage which is available at our filter caps will be suddenly at our output terminals, where we normally expect our 13.5 or 13.8 whatever volt. And then our radio, which is connected to this power supply, is really jeopardized. Okay, and you may still wonder what I'm talking about. So let's look a little bit more in detail. So I've here my voltmeter, and when I now test the output voltage, so we can easily see it is 13.5 volt, and that is what we expect. So that is normally the voltage where we can supply our radio with. So no problem, our radios are certified for this voltage, so they simply work on this voltage. But now when I turn it around, we find here at the back of our power supply, we find here, okay, this is a heatsink, no question, but we have here on the back our power supplies. And remember our little schematic, we said that we have a different voltage at the collector of our power transistor, and the collector of this power transistor is here. And now you may already see what I mean. So we have 31 volt present at the collector at our power transistor. Yeah, and coming back here to our little schematic, I was just probing the voltage here at this point. So this is the collector of our power transistor, and we measured 31 volt, and at the emitter we want 13.5 volt, what we have, no doubt. But it happens from time to time that for any reason this power transistor is failing, and failing means it could happen that it is shorting out. So that means we have really no resistor between collector and emitter, and that means that our 30.1 volt we was already here measuring at the collector is then present at our output terminals. And you may already imagine, when I have 30.1 volt at our output terminals, then that is directly feeding our radio, and our radio are not built for 30 volt, and that means with a voltage like this we are really killing our radio, because of course in our radio we have also voltage regulators and many components which are directly connected to our 13.5 volt. And you may understand, if we are now feeding these components directly with 30 volts or maybe even more, it depends always what the transformer is delivering, then you easily kill your radio, and a lot of components will blow in your radio, and that really will be a very expensive repair. And therefore we just want to think about what can we do to avoid this transistor failing. We do not want to think about what can we do that this transistor don't fail, because we can't do anything against that. But what we can do is to add a little circuit to our power supply, that in case our power transistor is shorting out, that then this high voltage will not have a chance to get to our to our radio, and that is what we want to look into, and that is what we want to build. And yeah, that is something we want to simply add to our output terminal. So additional little circuit that is able to avoid this high voltage of 30 volt or such, will be able to get through to our radio. Well, and there is already a circuit on the market which is very sufficient in protecting our radio, so that is nothing new. I just want to bring back this circuit back in your mind, and I just want to show that it is really easy to build, and we will come in a second to this little circuit. What I just want to do is using a box like this, and we just want to make this box that we can use it here in front of our terminals, and that we have a so-called thyristor crowbar in our circuit, in our plus line. And this thyristor crowbar will be able to short our then 30 volt or more in case that our power transistor is failing, that we have a crowbar, a thyristor crowbar, what will then short this 30 volt to ground. And if we are shorting our plus terminal, which is then feeding 30 volt or once feed 30 volt to our radio, if we then be able to switch that back to ground, then we avoid this 30 volt going to our radio. And with this short, it is a kind of artificial short, what we gonna produce, we will simply blow a fuse which is also in line, and then the thyristor and the fuse will together be able to protect our radio. And that is the idea, that is the aim, and yeah, I just wanted to show you how simple it is to build a little circuit like this, and it is not expensive. We only need a few components to build it, and yeah, let's go into this schematic, and you will easily see that it is really easy. Yeah, and here is our schematic, and as you already see, it is really very simple. So we have here our input, which is at least nothing else than here our power supply output terminals, which are going here into our little thyristor crowbar. We have here a fuse, and we have here a thyristor. And the idea is, as you can already see, this thyristor is connected from our plus line to ground. And if this thyristor will switch, that means that from anode to cathode we have a low resistor, or we have a low voltage drop, then that means that we have a current flowing here from our plus line to ground. And that means if we have a current flowing which is not regulated by resistor or such, we will really have a big current which will go to ground. And then we have here a fuse, and this fuse will blow immediately and will switch off our 30 volt, which is now coming from our power supply caused by the defective power transistor. So that is the idea, and the only thing we need is a thyristor which is able to handle our 20 or 25 amps, which is normal when we connect a power supply to a 100 watt SSB radio. So we need approximately 20 to 25 amps. So it depends a little bit on the radio, but approximately 20 amps is what a radio, a 100 watt amateur radio is consuming. So that means that this thyristor must be able to handle this 20 or 25 amps, and this thyristor needs to handle this current until this fuse here has blown. And if this fuse is gone, you see our plus line is interrupted, and we will not have the high voltage at the input terminals of our radio, and that will then protect our radio for going faulty. I mean, this does not help our defective power supply. I mean, still our power transistor is defective, and in our case it is shorted out. So our power supply needs, of course, a repair, so no question. But I mean, it is much easier to replace a power transistor, and the power transistor is anyway broken, so we need to replace it. But I think it is much better to have a circuit like this, which will protect our much more expensive radio than you know, having nothing in between. And we know that in the case our power transistor is failing, you know, that then this linear power supply is really killing our radio. So I think thyristor crowbar is really a good idea. I mean, beside the fact that these transistors just shorting out, the other what can happen beside shorting out is that in the event of a failure, this transistor goes open. I mean, if a transistor, a power transistor, goes open, no problem whatsoever, because then the voltage, the higher voltage from our filter caps can't pass through and cannot jeopardize our radio. So it is only the case when these transistors are shorting out. And believe me, this happens, I will not say quite often, but I have had it much too often. And I think yeah, to have really a broken radio, it is much better to implement a little circuit like this, and this circuit is easily able to protect our radio and is able to avoid our radio for go broken. Okay, so what we gonna do right now, we take this schematic and we build it on a breadboard, and we just want to check out if this circuit is really working. I mean, you see we have here that diode, we have resistors, and we have here a little capacitor, and of course we have here our gate. And you may already know that if we have a positive voltage at our gate, in that moment this thyristor switches on, and then we have a low voltage drop between anode and cathode. So therefore, once switched on, we have always this current way, this current pass, and it is good to have a fuse which will then blow, because once again this is of course an artificial, a wanted short, and this short means that if we have a 20 amp power supply, this 20 amps will flow, and therefore it is good that fuse will interrupt this current flow. And normally we have a fuse here in our power supply, and this fuse, which is normally switched to the primary side of our net transformer, will blow. So that is what this fuse was made for. But just to be 100% sure, we add a second fuse here into our Crowbar plus line, just to be sure that minimum one fuse will blow, either this here or that. But what we definitely need is one fuse which has to blow. And therefore, yeah, let's put it on a breadboard just to see how this circuit works, and then we can start to bring it into a little case, and we will then at the end be able to connect it in between our power supply one hand, and on the other hand our radio. We put it in between and do a active protection for our expensive radio. Okay, and here is our test circuit already on the breadboard. So we have here our thyristor, and we have here our Zener diode, and we have our both resistors and this capacitor. So this circuit here on the breadboard is absolutely following our schematic, which we have of course here. And what you can see as well, so we have our power supply connected to our thyristor Crowbar circuit, and the power supply, as you can see, is delivering 13.8 volts. So that is what we have talked about. And this meter here is probing our voltage at the output of our Crowbar, which is finally here. Okay, so now I have added here some values, and well, I mean, it is clear that this little thyristor which is here on the breadboard is not able to handle our 20 plus amps. So this is just for testing purposes. We definitely need a much bigger thyristor. So this one can handle, I believe, 3 amps or so. So this is definitely not the right one. But it will help us to understand this circuit, and it will help to understand that we really have not many components, and it is really easy to build this circuit. Okay, so going back to our schematic, just a little more background information. So we know that a thyristor will switch on when there is a gate current present, of course, at the gate. And therefore we have this voltage divider consists of this Zener diode, and I've chosen a 15 volt Zener diode. This resistor down here, which is basically controlling the current through the Zener diode, and this gate resistor, which is finally controlling the current to the gate and through the gate. And we have here as well a little capacitor, and this capacitor is nothing else, together with this resistor, a low-pass filter. This low-pass filter is really important because when we switch on our power supply, or if there are peaks on the line or such, it might happen that there is a pulse occurring here at our, let me call it input pass to the gate of our thyristor, and you see that then we have here our low pass filter sitting, that the pulse will be attenuated and cannot really influence here our thyristor, so this pulse never should make our thyristor switching on. So that is the idea of this resistor and this little capacitor. So now, if our voltage is increasing 15 volt, because this is a 15 volt Zener diode, then this Zener diode starts getting consuming current, and that means that at this point, I mean, we always will have a 15 volt drop here at our Zener diode, but we have seen that at our filter capacitor inside our linear power supply, we have 30 plus volt present, and that means that of course we have here our 15 volt voltage drop, but even with 16 or 17 volt here at our Zener diode, we will then have here with this with this voltage divider 1 or 2 volt already here at our divider resistor, and with only 1 volt here at our 470 ohm resistor, we will already have this thyristor switching, and that is very good, because that means with already 16 or 17 volts, which would otherwise go through our radio, this thyristor will switch and will then short our voltage and our current, which is coming from our power supply, until this fuse will blow, and then everything is switched off, and our radio is safe, and of course our little thyristor crowbar is safe as well, because we don't want to really blow our thyristor, so that makes no sense. Okay, once again, it is everything exactly as we have it on our schematic, And now if let me see if we really can see both. Yeah, you should be able to see here our voltage at our power supply, and you need to watch this voltage at the output of our circuit as well. So we should really observe both. And what do we expect right now? So in our case, I'm gonna increase this voltage here at our power supply, and of course I do it here with our pots. So I'm increasing the output voltage, and that is then very similar to the event of a failing power transistor as explained before. And when we are increasing 15 volt, then of course we expect at a certain voltage overall that then our thyristor will switch on, and then at this meter our voltage should go down to, I don't know, 1.5 volt or 1 volt, so that is the drop voltage of our thyristor. And we will see here that we really have a short, so this power supply is set to, I believe, 2.5 amps, and that means we see that we have here our full power, which will be drawn by our circuit. But the important point is that at our output there is no voltage present any longer, and that is the important point. I've not installed fuse here in our test circuit, but normally our fuse would then blown and everything would be fine. That will not happen here in our test circuit, because we just want to really see what's gonna happening if we increase our voltage. Okay, and have relocated here my both devices, and now so that you can see both voltages, I go and increase here my output voltage, and you see already that we have now a short. You see here we have only 1.4 volt present at our output. So once again, this is now the voltage which will be available at our radio, and we know 1.4 volt is not harmful. So if then the fuse is blown, this will be gone as well. But you very nicely can see that this is now here the short, and our radio is protected. Now I go back here with our voltage, and I have to set the thyristor back into working condition. So that is what I've done, and once again you see now it is set to 8.5 volt, so we know we are operating with 13.5, 13.8, whatever, and yeah, so now both voltages are present. Our radio gets supplied, no problem at all. And now I do it once again very, very slowly. I increase the voltage, and normally if there is a power transistor shorting out, this voltage will come very quickly, so that is a voltage rise by sudden, and I just simulate it here very, very slowly. So, and you have seen it, boom, there we have already our switching point. So it was, as I have seen it right, it was already below 15 volt once again. Very slowly. Where is our switching point? Here is it, 14.6, and that is really brilliant, because we don't want voltage higher than 13.8, maybe maximum 14, so that is just fine. But we really want to get the voltage switched off at that point, which we have seen here on our power supply. And once again, this is of course the voltage which is for the moment in time present at our radio, but with a blown fuse it will be gone as well. And you really can see pretty easy that this little circuit is working just fine. And once again, that is all we need. It is really simple. Okay, and that means that our circuit is really working fine, beside the fact that this thyristor is not capable to handle our 20 amps plus, and therefore I have here a very nice thyristor, and that is a BTW69/800. So this is a thyristor. This is a really power thyristor, and this one is really able to handle our high amps, our 20 plus amps. So that is what we need, and therefore this is the right component for our purposes. And here we have the data sheet of our power thyristor, and yeah, this guy is able to handle up to 50 amps, and in average it is able to handle 32 amps. So that really means our component is the right one to do the job. And well, now the next will be, we will check it out in our test circuit, and if it works in our test circuit as good as our little test thyristor, then we really can go and build our final circuit. Alright, and as discussed, I have now the new thyristor here in our circuit, so don't be confused here by this cables and clips. It's just that I have the thyristor here connected to our circuit, and yeah, we just wanted to check out if we have the same behavior with this big power thyristor. And yeah, everything is prepared, and again I have here our two voltages which are of importance, and you see 13.8, which comes from our power supply, and here again the voltage which is available, let me call it, at the output terminals into the direction of our radio. And with the new thyristor in place, let me increase the voltage, and you see it is just switching at 14.1 volt, which is very nice. So with the new power thyristor, it is sensitive enough, but I had to do a little adjustment. So I have changed this 100 ohm resistor into a 33 ohm resistor. So that is because this power thyristor needs a bit more gate current, and therefore I have simply reduced it to 33 ohm, and that is how it is built right now here on our breadboard, and here our power thyristor. And yeah, it is just working excellent, and therefore, yeah, we know our circuit is fine, and that means let's put here our components onto a little proto board, and let's put our circuit here into a housing like this, and then we have the device which we want to switch between our power supply and our radio to protect our radio. So let's go ahead. Okay, and I'm just starting here with some mechanical work, so I have to fit in this proto board here into this little housing, and of course we need to bring somehow here our thyristor into the housing, and yeah, put here terminals on and such. So now I will do some of this mechanical work, and yeah, when I have something more exciting, I will come back, and we go then ahead step by step. Okay, just giving you an update. So I'm just planning here the proto board. So I have done all the connections which are needed here on the board for our components. And yeah, I have done the first mechanical work, so that we can put this PCB here, or this proto board, so that is the better word for it, that it fits into here. And yeah, now we really need to make our through connection. So that is here our both power lines. So we know that we have running here 20 amps plus, so we really need to do something which is really able to handle this 20 amps, and yeah, that is a wire like this, and I plan to put the wire here over the board, so then it runs here over the board, but we really have enough copper that this little circuit is really able to handle our 20 plus amps. So yeah, that's a little update, and stay tuned, I will be back. Yeah, currently I'm implementing here our high power through connection, so that needs to be soldered here on the board, and yeah, let's go ahead. Well, and you see we are making some progress. So the little board is more or less ready. So I have here our high power wires, so which goes through. So this here will then be the input from our power supply, and here at this side we will have our output towards our radio. So here I will implement a wire which I can easily connect to my power supply, and on this side, yeah, I need to think a little bit more about it, but I try to get these terminals in if it fits. If there is enough space, and I guess I will put this here in, and yeah, so we are getting closer. Okay, before I start now installing the terminals and everything, to make it really clear what I have done, so this wiring here is really a big lead, and it goes here really completely under the PCB or proto board. So you know, we have really this way through that we have always this big wire that really our 20 amps can be handled. So just before I now start and really connect everything, and we can't see it any longer, so I hope it is now a bit better to understand how this is done. Yeah, because I say it again, we really need this big wire, otherwise we can't draw this high current. Okay, nearly done. So wiring is almost done. So connectors are connected, and this here is now the wiring for our thyristor, which needs to get installed here into our little project box, and then it is more or less ready. So let's go ahead. Okay, so our wiring is more or less done. So we have integrated here our thyristor, and thyristor is connected here to our input leads. The green wire here down here is the gate of the thyristor, and these both are our output terminals. Well, the only challenge here is that you really have to handle these big wires. I mean, first of all, these wires which will lead approximately 20 plus amps, and as well our output terminals. And yes, these connectors could be bigger, but I didn't have the right one on stock, so I just choose this here to demonstrate it. I mean, it will work, but it could be better. Secondly, I was interested to get it all in this little project box, so that made it more difficult, so you can easily choose a bigger box, so then you have more space to get all your connections, so that makes it easier. And of course you can put the whole circuit inside your linear power supply as far there is enough space, and there are not warranty issues or what have you. So once again, here I was really interested to get it in this little small box, and that is somewhat challenging, and therefore if you decide to do it as well into such a small box, yeah, you have to consider the big cables here, the big diameter, so that is definitely a challenge. Then secondly, I do not have an inline fuse right now, so I just told you I want to have inline fuse as well, and that is what I will definitely do, but I do not have it on stock, so I have to rely on the primary fuse in our power supply. And yeah, if the power transistor failed in your linear power supply, your complete electronic is not working any longer, and that means your shorted protection, which might be implemented in your power supply, will not work as well. So therefore your primary fuse will work and the primary fuse will blow. So it is not absolutely necessary to have a second fuse here inside your in line with your plus line, but I personally prefer it because I have then a better control, and I can choose you can choose the fuse if you use it in a smaller power supply or what have we. So I will definitely put a fuse in line, but as I said, your fuse in your power supply will do this job. Yeah, once again, these terminals could be more rough, and that is something you should consider as well. And well, what you always have to have in mind is when you are handling 20 plus amps, the risk that it really gets hot, and that there is a potential risk of a burn. You need to be really careful. You need really know what you are doing. So if you are doing this project, you're really doing it on your own risk. So take care and be aware that you are handling a really high current, which really can cause burn, and that is what you really have to have in mind. But so far we are now ready to test here our circuit, and yeah, if that will work without a problem, then this little project is ready, and I can directly then connect it to my power supply. Okay, so circuit is ready for testing, and yeah, I have already connected here my electronic load to the circuit. I just want to draw some current here through our little box, because that is what this box normally need to do. So it needs to be a connection between my power supply and my radio. So that means there will always be a current flow, and that is what we want to simulate. On the other hand, I have already connected, and you can't read my meter here, so let me see if I can do it any better. So that is yeah, 12.7 and 12.7, so that is the voltage which is now present at our little crowbar. And this meter again is reading the output, and of course our power supply is telling us what is fed into our circuit. And additional to that, I have here my electronic load, and the electronic load is also connected to our power supply. And when I now switch on here our load, you see it is set to half an amp, and you see that is 6.3 watt, and we see our output voltage is there, and you see our half an amp is drawn through this little crowbar. So that is what our power supply is telling us as well, half an amp. And yeah, I just want to increase it here, let me say to an amp. I mean our power supply, our lab power supply here is not capable to deliver 20 amps, but that is not needed. As long we see that it is working even with 1 amp, because yeah, so that is, that is more or less the receiver current. So maybe we can even increase it to 2 amps, because that is what our receiver normally will draw in receive mode, of course not in transmit. So that is more or less real condition what we are simulating here. And of course this meter is reporting 12.5 volt at the output terminals, and our electronic load is reporting 12.4, so that is clear, because we have the wiring in between, and of course we have a little voltage drop as well at our wiring. And voltage drop always means be careful, is there maybe a bad connection, because that can also be the case that there is a bad connection. Bad connection always means you have a resistance at this bad connection, and that means it could get very hot until it starts burning. So that is what I always want to lead your focus to. Beware of bad connections or such, because that is always a risk that it starts burning. So that is very, very essential. Okay, other than that, it is all working just fine. And now we are interested what would happen if we have a failing power transistor in our power supply. Okay, and I've reduced our current, which is currently drawn by our electronic load, because this power supply is only set to 2.5 amps. And we just want to check out if our crowbar is working fine. So therefore I reduced it. So it is not essentially necessary, but to have a better overview what we are doing here. So we leave it in this mode, and we are drawing current through our crowbar box. And now let me simulate a failing power transistor in the power supply, and that is what we can simulate as we have done it when we tested the circuit on the breadboard, when we simply increase our voltage, our output voltage. I mean, it is clear when the output transistor, the power transistor, is failing, you have a sudden jump up to what the power transformer in your power supply will deliver. So it is not this slowly increasing voltage. So this is lab condition. But if we are able to reproduce it here under lab condition, we can be sure that in real life, when we have this voltage jump up, then we can be sure that our thyristor crowbar will short it, and that we will not have any voltage present at our radio. Okay, so let's try. Let me increase it, and we know somewhere around 14. And here we are. And we can see that is now the voltage at our radio, and going up here to our electronic load. So you see 0.8 volt is the voltage which is present at our radio. And that is not harmful, even if our power supply is blown and the power transistor has shorted out, we are now sure that nothing can happen to our expensive radio. And that is exactly what we wanted to have. And therefore, we can say that our little circuit here is working just fine. Great! Yeah, and as I already told you, I have done minor changes here in our circuit. So with the new power thyristor, which we have chosen, our BTW69/800, so that is a power thyristor we are using. And therefore I had to reduce here our gate resistor from 100 ohm down to 33 ohm. So that is one change. And the second one is I reduced our Zener diode from a 15 volt type down to a 13 volt type. And so in this configuration it is showing the behavior what we have experienced a minute ago. So therefore that are the changes when we use our big power thyristor. And down here, so this is for the proto board, my little diagram, how it is connected on the proto board, and this green crosses is where I disconnected my my copper on the proto board. Yeah, if you don't know what I mean, so we have this copper here, and you see that it is not interrupted somewhere, so you need to go manually to the point where you need an interruption, and you simply drill it out, and that is what I've indicated here with my green crosses. So of course if I put a diode here over this board, right, and then this diode is of course shorted by the copper here, and therefore for this kind of boards, proto boards, you just interrupt it by drilling it out. So that is what it is meant with this. But if you are using a different proto board like this here, so a situation is definitely different. So that depends on the proto board you are using. But you can also produce your own little PCB, so that is also possible. So that depends on your preferences. It is just that you know what I have done here. So that is definitely all what it is. It is really a very simple it is very simple schematic, and it is not too many components, so that is a weekend project. And as I already said, the only thing is that you have to handle really big wires. Yeah, now the only thing is I can now close here my little box, right? And that means our project is ready. Everything is fine. I will finally install my fuse in line, as I already discussed it. And that's it. A really nice weekend project, which will help to protect your expensive radio, and that is always worth to do it. Okay, so that's it for today. I hope you enjoyed this little video and the information, and yeah, thank you for watching. And if you like this video, please give me a big thumb up. Subscribe if you didn't have subscribed yet, and catch you next time. Bye!